Hi, I'm Ciaran. I'm a fourth year Bachelor of Music student at UBC studying French horn and minoring in applied music technology. In this video, I'm going to give an overview of my capstone project, Quicksand. I'm a programmer. I'm really passionate about audio programming as well as game dev and modding and also Linux. Once I graduate, I'm going to be applying for positions in all sorts of digital audio related fields with the ultimate goal of becoming a full time audio programmer. I have prior experience with audio programming in Max MSP, Faust, and Super Collider, but Quicksand is both my first VST and also my first major project in C++, which is super exciting. So, what is it? It's a real time granular synth. One of the frustrations I've had with granular synths in the past is that they don't offer much spontaneity for the user. While a traditional granular synthesizer operates on a pre recorded buffer, Quicksand takes live input, making it more of an audio effect than an instrument. Now I'm going to go over some of the hurdles that I had to overcome while developing Quicksand, as well as some planned features for the future. But if you'd like to skip to the demo section of this video, I'll put a timestamp up on the screen now. So, while working on this project, I've had to deal with several major challenges. Among these, I think coming up with an appropriate data structure for my VST's granulation engine and optimizing my code were the two most significant ones, but I'll cover a few more as well. When I was first conceptualizing the project, I had thought that I could use a generic circular buffer as my primary data structure, but when it came to implementation, I quickly found out that it wouldn't be so easy. For one thing, circular buffer implementations tend to make reading a destructive process, like in a stack, which can work okay when you're dealing with a single voice, but once I introduced polyphony and also random access, it just wasn't sufficient. Most circular buffers are designed to prevent the head from overwriting the tail, and they do this by making the buffer size expand as you fill it and contract as you read samples out. Um, Instead, I needed a data structure that, once filled, would constantly overwrite itself without introducing errors when you try to read a grain. For this reason, I decided to write a data structure that I called a rolling cache instead of using a circular buffer. Instead of using a head and tail pointer like a circular buffer, it just uses a head pointer, which points to the most recently inserted sample, and a flag denoting whether the cache has been filled yet. This allows the user to read from the cache in a way that is indexed and also non destructive. Of course, all that my cache does is store incoming data, so I needed to granulate it. So I built a granulator class, which essentially just pulls out grain-sized chunks of data from the cache and then applies an envelope to each grain and stitches them together. One of the major challenges here was dealing with situations where a grain might be split between two audio blocks. I've mitigated this using a struct that I called a grain overhang. Essentially, it just preserves the remainder of the grain so that no data gets lost. This gets a little more complicated once we start dealing with overlapping grains, but it's not too bad for the most part. I also have a multi-granulator that wraps 16 instances of the granulator, providing polyphony. One of the more pernicious bugs I had to deal with in the development process was concurrency related. When playing multiple voices, the granulators would desync with each other because of changes in the parameters. As a result, now my processing thread only pulls in parameter values at the start of each block to keep all of the voices synced. Debugging this issue, though, was not so easy because I actually didn't know whether it was coming from one of my classes or if it was coming from a concurrency problem, right? So I wrote up a pretty fully featured test suite for the VST, which rigorously tests all of these classes, the rolling cache, the granulator, and the multi-granulator, to ensure expected behavior. More recently, I've been focused on optimization. So when I was first prototyping, I had vectors allocating memory all over the place, not realizing how problematic that can be. Uh, Now, the maximum required memory is all allocated up front, and we just work with that, which has made the plugin vastly more reliable. On the CPU side, Quicksand does a lot of iteration, and minimizing the number of times I'm iterating in each block is a huge priority going forward. This is the first project I've ever worked on where I've really had to worry about the coefficient in my runtime complexity. Even though most of what I'm doing is at O of n, there's a real time crunch each block, so every iteration becomes significant. I've got a fair bit more work to do on this front before I add any like fancy new features. For instance, right now Quicksand applies envelopes to each grain on a per voice basis, but if I can pull that logic up to the granulator level, I'll be able to reduce the number of iterations by a factor of 16 in that section. Speaking of planned features, there are a lot of them. One of the big ones I would like to add is BPM synchronization. This is going to be a major challenge, but I think it's super useful and would make Quicksand a lot more versatile in the average use case. I'd also like to add per voice pitch shifting of some sort. I know a lot of granular synths implement that, and it's really fun. Although I've yet to decide how I want to do it. There are also some quality of life features that I think would be really useful. For instance, right now the granulator outputs silence while the cache is filling up. I'd like to change that so that it can granulate over the cache as it's filling. You can also check the README on GitHub if you want to see some more features that I'm planning to add. So with all that out of the way, let's get into the demo. All right, so here we are in Bitwig, and for demo purposes, I'm going to start out by showing you just a simple C minor triad saw wave coming in and just kind of show you what each parameter on Quicksand does. So you can hear the wet signal is just a straight triad sustained, right? And then as I go into the dry signal, you start to hear this amplitude modulation. We're at an 80 millisecond grain size, and as I adjust that, slows down, speeds up. I'm just going to set it back to the default for the time being. Now for the shape, you can harden or soften your grains, and I have a minimum of 5% just because at 0%, which is just a square, you get pops and clicks and all sorts of bad stuff. And then randomness you won't actually hear in this example because it's just a straight saw wave, but what the randomness parameter essentially is doing is determining how far back in the cache grains can randomly be pulled from, and I'll demo that with the next example. And then overlap, you can hear they're becoming more detached, and now the grains are overlapping, which gives you this really cool kind of detuned saw sort of sound. I'm just going to change that back to the default as well so that I can demo polyphony. So I'm going to change the voice count to 2, and you can already hear you're starting to get this sort of super saw, right? And with this particular example, you don't actually get that much difference between, 16 voices versus two voices, but you'll hear with the Mahler example that it's much more significant. But one of the really cool things with a saw is if you reduce the overlap, you start to get this almost like arpeggiation effect, which, I don't know, I find it really interesting. I think it's from all of the phase cancellation, right? Okay, so that's your saw. I'm just going to deactivate that, and let's talk about Mahler. So I'm just going to start playing it. I'll play it, it's an art song from Rickert Leader, I believe, and I'm just going to play it completely dry for a few seconds so that you know what it sounds like. Okay, that's probably sufficient. Now, if I just show you it running through Quicksand. This is with one voice, of course, these are all the default settings. I'm gonna crank up the cache size, and you'll hear, as I mentioned in my intro, when I adjust the cache, it has to totally refill, so it's outputting silence, but now I have 5 seconds of cache to work with now that it's filled up, right? So as I adjust the randomness, at 0%, you can hear it's just playing it completely straight, but at 100%, you're dealing with data that could be anywhere in that 5-second cache, right? Now, the voices actually, each voice has its own randomness, right? So as you increase the voice count, you get kind of a homogeneous texture from all of the randomness, and as I pull the randomness back, it becomes more uniform, right? I think with a little bit of delay and reverb, and with the overlap at minimum, you can get some really cool kind of droney effects, especially if you modulate the randomness here. It's pretty cool. I think that's about it for my demo, actually. All right, so I hope you found that interesting. I'd just like to make a few more notes before we end the video. Firstly, a huge thank you to Dr. Keith Hamill, who oversaw my project. He's been an invaluable resource for me, and I sincerely appreciate all of his help. And finally, check out Quicksand on GitHub. I'll put the URL up on screen right now, so if you'd like to install it yourself, contribute to the project, or even just tell me where my code could be improved, I'd really appreciate that. Thanks for watching.